Hello, I'm Ronan, and this is an explanation of the dynamic programming technique. So first, to understand dynamic programming, it's useful to recap recursion and the divide and conquer method. So at the top right here, we have just a simple recursion for computing the factorial of a number. So the factorial of n is just n times the factorial of n minus 1. So here, we've broken the problem into a subproblem, and this subproblem is strictly smaller than this initial call here. And we also have a base case that the factorial of 0 equals 1. So this is all the information you need to compute the factorial of n just by this recursion relationship. So here we have a divide and conquer, which is merge sort, just a high-level representation of it. So the merge sort of this array, you break it down into two subproblems where you split the array in half, and you merge sort the left half, merge sort the right half, and then you'll merge the two halves together and get the final array. And so the important thing here is that we'll take the problem, and then each of these subproblems here is a smaller subproblem, and it's independent from the other subproblems here. So dynamic programming is very similar, except these subproblems may overlap. So in this example, it might mean that sort of multiple subproblems will reference the same array indices. And the key to solving these dynamic programming problems efficiently is going to be using memory to store the solutions to these subproblems and to sort of look up the solution to the subproblem rather than recomputing it each time, which is inefficient. And I'll get into all that later. So this is the problem I'm going to go over. It's Leetcode problem number 64. So given a grid filled with non-negative numbers, the goal is to find a path from the top left to the bottom right, which minimizes the sum of all the numbers along the path. And you can only move either down or to the right from any square. So this example, this is the minimum path sum. And for example, like this other path would be valid, but it just has a larger sum, so it's not the minimum. So the way, the first way we're going to look at how to solve this problem is to use recursion. So given our goal to go from the top left to the bottom right, we're going to break it down into subproblems, and the subproblem is just going to be a different starting square. So essentially, if you're starting at this square is going to be your initial state, and then a subproblem would be starting at this square and going down to the bottom right, or starting at this square and then finding a path to the bottom right. So we're going to define some optimal cost for a path function, just call it cost. So overall, we're looking for cost evaluated at this top left square. Our base case is going to be that the optimal path cost evaluated at the bottom right is just going to be this one square, because the path from the bottom right to the bottom right just consists of this. So it's just going to be the value of the grid at the bottom right. And so for our recursion relationship, the cost of a general square with a row and column, say this one, for example, is going to be the value of the grid at that square plus the minimum of 2 recursive calls. And so if you remember, there's only 2 things we can do here since we can only move down or right at any point in time. So the minimum cost function, we're going to compute recursively. We're going to say cost of this square right here, or the cost of this square right here. And so this is a full solution to the problem, just like the previous examples we went over. So there's a problem with this naive brute force way of doing things, is that the cost of this square is actually computed twice. So for example, these lines sort of indicate the flow of control of the program. So if you do a recursive call to here, it will do a recursion call on this square, and then this will do a recursion call on here, and likewise with this other path. So since our program has no way of basically remembering the previous solutions to the subproblem or sort of remembering what the board looks like, it's going to do extra work. And so this example, only really these squares, a few of the squares are computed twice, so it doesn't seem too dramatic. But actually, when you have larger boards or different dynamic programming problems, this extra work can be the difference between exponential and polynomial time complexity. So it really makes a large difference in actually solving these problems in the real world. So our solution is going to be tabulation or memoization, which are related but different terms. I'll go into that later. So essentially the core idea is that with our naive approach, see we had function calls for this recursion relationship, but with tabulation is what I'm going to go over. You replace those just with this array access. So for example, like with this flow of control here, you would go through these recursion calls. And then once you reach this square, you just have these red numbers all stored in memory. And you just look up this value, which is 7 here. And then same thing for this one, you just look up this value so you don't have to recompute it. It's just already sitting there in memory. And so our sort of array is just going to be a grid called opt, which stores these red values here. So first we have these base cases. You sort of have to look at the problem and you recognize that you can only move right or down from any position. So like we said earlier, the bottom right here, there's only one square in this path, but along this column, you can only move down, you can't move right. So there's only one option. So you compute the base case, sort of like the cost of the minimum path is just the cost of the only possible path here. And so this is an implementation. This essentially defines the base cases along the rightmost column and this bottom column here. And so then our recursion relationship is going to be dealing with only these squares that are not on the base case, essentially. So our recursive step, as we've shown earlier, it's using these array accesses. So it's looping through, like I said earlier, just these 4 squares, not these squares which we've already computed as the base case. And so, for example, here we're just computing it as the grid at this square, which is going to be, so this value is going to be 1 plus the minimum of the stored value below it, which is this red number 8 here, and the minimum with that compared against the stored value of the right square, which is this 6 here. So here, this computation is going to be 1 plus the minimum of 6 and 8, which is just 1 plus 6, so our value is 7. And so that is correct and corresponds to the solution that we saw earlier. And our desired result is going to be opt, which is this array of red numbers at the top left corner. So the dynamic programming strategy I went over is called bottom-up tabulation. So the whole strategy is you define the subproblems, and then you define the recursive relationship between the subproblems that build to larger subproblems, and then you define the base cases over here. And so you compute the base cases explicitly, like I showed earlier, and then you create the array opt, which is going to hold solutions to all of our subproblems. And so the bottom-up part of this approach is that starting just after the base cases, we're going to iterate and fill in the arrays. So essentially, like this is 2 nested for loops instead of a series of recursive calls, because we're just going to compute all these red opt numbers for all values greater than the base cases. And then our desired result is just going to be the opt at this top left corner here. So that's why it's sort of bottom up, because you start at the base cases and go up towards the solution that you actually want. And so this is going to reduce that overhead of recomputing these repeated values here. So a different dynamic programming strategy, which I didn't go over in detail or implement in code, I mean, is top down. It's called memoization. So that's when you start with a function call for the overall solution and you do it recursively. But every time you encounter a subproblem, so for example, you encounter this right subproblem here, you check if you've already encountered it before. And if so, just return the memorized value. And if not, add it to memory and then return that value. So this is going to give you the same answer, but it is going to potentially save some work in some cases of dynamic programming problems where not all of the solutions, not all the subproblems are invoked for every overall problem. So yeah, in conclusion, there's different ways to implement this with different space complexities, which I didn't have time to get into, but it's something to look into in the Leetcode solutions if you're interested. Dynamic programming is sort of a form of brute force, but you do the minimum possible work because you're reusing the results of the subproblems. And you can bring exponential time problems to polynomial time. It has many applications in these important algorithmic problems from various fields, but the core idea is that you use overlapping subproblems. And that is it. Thank you for listening.